Greenland can look larger than South America on a familiar rectangular world map. But Greenland is not secretly a continent-sized rival. The picture is stretching it. The real mystery is why a map would choose that distortion on purpose. A globe keeps the geometry honest, but it is awkward to fold, print, tile, or display on a flat screen large enough for continental comparison. Turning a curved surface into a rectangle demands a map projection, a mathematical rule connecting globe coordinates to paper coordinates. No rule preserves area, shape, direction, and distance everywhere. Each projection decides which errors to tolerate. Distortion can be redistributed, never erased. The projection makes a very specific bargain. It protects tiny local angles and shapes. Its meridians become parallel vertical lines, while its parallels remain horizontal and meet them at right angles. That neat orthogonal grid is deliberate. That clean grid is not a photograph of Earth. It is a coordinate machine built for a job. In 1569, presented the projection on a large world map intended for navigation. Sailors often follow a constant compass bearing, tracing what cartographers call a rhumb line instead of continually changing course. That curving route across the globe becomes a straight line across the chart. Straight does not automatically mean shortest. Most rhumb lines are longer than the corresponding great circle route, yet a straight chart line makes one constant bearing easier to draw, measure, and follow with ordinary chart tools. For navigation, the projection spends area accuracy to buy useful angular behavior. The price begins with the latitude grid. Meridians converge on a globe, but forces them to stay parallel, creating artificial width at high latitudes. To preserve local angles, it must stretch north-south by the same amount as east-west. Unequal stretching would deform small local shapes, so the horizontal latitude lines spread farther apart as they approach either pole. On a spherical, the local linear scale follows the secant of latitude. At the equator, the factor is 1. At 60 degrees, it is about 2. At 70 degrees, it is about 2.92, and at 80 degrees, about 5.76. That factor acts in two directions, so area grows roughly with its square. Doubling both width and height quadruples the patch. At 60 degrees, a tiny patch is drawn about 4 times its equatorial area at the same nominal scale. At 80 degrees, the local area enlargement is roughly 33 times. This is why high-latitude land seems to inflate. Greenland sits mostly far north, where the scale multiplier is already large, while equatorial regions stay near baseline. Notes that Greenland is only 1/8 the size of South America, though can make it appear larger. The map has preserved local shape while sacrificing any fair visual comparison of continental area. The distortion does not suddenly start at Greenland. Every latitude receives its own scale factor, regardless of borders or national importance. Cities near the same parallel are enlarged similarly, while tropical places stay much closer to equatorial scale. A world map hides those local multipliers inside one apparently uniform rectangle. Keep moving north and the scale factor rises without limit. At 90 degrees, the mathematical distance to the pole becomes infinite. That is why a complete map cannot show either pole at all. Modern online maps inherit a related version called Web, registered as EPSG 3857. Its rectangular coordinates divide conveniently into repeatable square tiles for zooming and panning. Each zoom level subdivides the same grid predictably. The familiar web map survives because this geometry is operationally convenient, not because it preserves global area. Web is also a technical compromise. It applies spherical projection equations to ellipsoidal Earth coordinates. EPSG documents scale differences and northing differences relative to world. For visual web mapping, that trade is accepted, but it is not a precision geodetic promise. A finite web map usually stops near 85 degrees north and south. Beyond that cutoff, the race toward infinity would consume tiles without ever reaching the pole. The missing polar caps are another clue that the rectangle is a tool, not a literal flattened globe. So should every world map abandon? Only if every map has the same purpose. A useful chart can still be a poor area poster. A navigation chart, a street map, and a map comparing population density ask different geometric questions. Projection choice is not a beauty contest. It is a decision about which measurements must remain trustworthy. For thematic world maps, an equal area projection keeps regions proportional to their real surface area. Equal Earth was designed for that task and is appropriate when area comparisons matter. But equal area does not preserve every shape, direction, angle, or distance. The trade-off moves rather than disappears. A compromise world map can distribute distortion more gently without making one property perfectly correct. A local topographic map can choose a projection centered on its region and keep nearby errors small. The honest question is never simply which map is accurate. It is accurate for what job and where? Return to Greenland, and the visual trick now has a mechanism. Its northern latitude multiplies local linear scale, and area enlargement squares that multiplier. Preserves useful local angles and straight rhumb lines, while polar area grows dramatically. So why does Greenland look huge? The map is protecting navigation geometry, not comparing land area. The distortion is not a hidden mistake. It is the visible cost of the projection's chosen job. Subscribe for the hidden reasons behind ordinary things, including the rectangles that quietly shape how we see the world.